Okay, so we're gonna we're gonna continue with current electricity. We're gonna try and get some concept clear. Okay, so again, when we talk about current, we're just gonna go over that. Current is the rate of flow of charge. Okay, so when we talk about a current flowing in a circuit, we talk about a charge moving in that circuit. And the current is the rate of flow of the charge. When we talk about the voltage or the electrical potential difference, that is usually the power source. All right. So the voltage, or the other term for it is electrical potential difference. That is the power source. That is what causes the charge to flow. You have to have a power source. You have to have an electrical potential difference uh, for the charge to flow. The charge is not going to flow unless you have that electrical potential difference. And we're going to go over this from time to time. So in order to have a circuit, you need to have a power source. You need to have a complete um, uh, conducting elements, okay? And you need to have a load. When we talk about a load is just like any device, any electrical device. You're talking about the light, the lamp, the washing machine, the dryer. Those are load. And those elements or those components, those things make up a circuit. If you have an assembly where you have the battery and just the wires without any electrical device, then that's what we call short circuit. You need some electrical device. You need some load for the electrical energy to be transformed into, say, light energy or mechanical energy. If you don't have that, then that's what we call a short circuit. So it's a circuit with a battery and wires without any electrical device. And you're going to have a high rate of energy consumption. The wire is going to get heated, and that can cause a fire. Okay? And the battery will drain very, very quickly. So, you know, this is the definition for short circuit, and we'll go over that. We'll go over it again, so don't worry about it. So this is, you have a power source, you have a battery, um, you have the positive terminal, the negative terminal, and you exclude the load. So so this is the load, the normal load, the light bulb. But if there's a short circuit and you complete the circuit by connecting the positive terminal to the negative terminal without the load, then the wires can get very, very hot. You drain the battery very, very, rapidly, and it can cause a fire, short circuit. So again, so when we talk about a load, it's just any device in the circuit. Circuit is usually equipped with electrical device. That is why you have a circuit. Examples are light bulb, motor, beeper, etc. Okay, the reason to have a circuit is to cause some device to function. Your compact disc, whatever. When you have a circuit, what you're actually doing is transforming electric energy into other forms of energy. All right. So when we set up our circuit, we have our power source, we have our wires, and we connect a load. So we connect a light bulb. Again, remember, the battery, all your battery is doing, or your power source, your battery or your power source is generating this electrical potential difference. So what it's actually doing is moving the positive charge from the negative terminal to the positive terminal. Okay? Again, your power source or your battery is moving positive charge from the negative terminal to the positive terminal. If you think about it a little bit, because you're actually moving a positive from a negative, the natural thing is for the positive to be attracted to the negative. So the mere fact you're moving it away and you're moving it towards a positive, the positive is going to repel it. You need external energy for that. And that is why, in order to get your electrical potential difference, you need energy. You have to supply energy. Okay? Just like when the power company put you on the power supply. All the power companies is doing for you is to give you electrical potential difference. That's all they're doing. They give you electrical potential difference. That is, they move the positive charge from the negative terminal to the positive terminal. And once you connect your wires, once you have an external circuit, then the charge is going to move from the positive terminal through the external circuit, that's the wires, and then it's going to come back to the negative terminal. When the charge move, it's creating electric energy. What it's doing, it's transporting electric energy. Okay? And that electric energy can be transformed into other types of energy: light, mechanical, sound, and heat. Okay? If you remember, when you have charge flowing in the circuit, when a charge is flowing in the circuit, okay, the 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 electric potential difference is dependent on the position of the charge. Okay, and we'll come back to that. But anyway, these are different type of loads you can put in a circuit. You can have your fridge, well lamp, computer, microwave. Anything you connect to the circuit is regarded as a load. You're going to transform the electric energy into some other type of energy. So again, we talk about the light, we talk about different mechanical devices, and you just connect it to the circuit. Now, we're gonna introduce another concept called power. And when we talk about power, in mechanical terms, power is the rate of doing work, or the rate of energy consumption. Okay, but in electrical terms, when we talk about power in electrical terms, we're talking about the rate at which electrical energy is supplied to a circuit or consumed by a load. Again, remember, when you have a circuit, the sole purpose of a circuit is to supply electric energy. Okay? And the rate at which you supply this electric energy, that is the energy per unit time, is the power. Okay? So you're going to supply this electric energy through the circuit. And if you have a load, say you have a washing machine, you have any type of electric, that's going to consume some of the electric energy. So the power of, say, the washing machine is the rate at which the machine consumes the energy that is supplied to it. Okay? So again, power is the work done on a charge, okay, or the rate at which the electric energy is supplied to the circuit or consumed by a load. The usual unit for power is watt. And because it's the rate of doing work, work is measured in joules, rate is in seconds, so Joule second is the same thing as the watt. Okay, we'll come back to that again, but just understand that powering anything is a rate of doing work, or the rate of consuming energy. All right, when we talk about the electric circuit, it is the rate at which electric energy is supplied by the circuit or consumed by any load in the circuit. All right. So if you have a bulb which is rated 60 watts, what it is saying is that that bulb is gonna consume 60 joules of energy every second. Okay, 60 joules of energy every second, as opposed to your 120 watt bulb, it's gonna consume 120 joules every second, because power is energy per unit time. Work done. The unit of work is joules. All right. And similarly, when we say kilowatt, kilowatt is 1,000 watts. Okay. Um, Again, so when you say kilowatt, it's 1,000 watts. When we talk about power, it is energy per unit time. Okay. The reason why I'm going to discuss kilowatt hour, when you get your electric bill, you're going to see on it kilowatt hour. So you know that watt is power, right? And this is power. And then this is kilowatt hour. So it is power. Kilowatt is, or watt is power. Power is energy per unit time. And then you're multiplying by hour, which is another time. So essentially, what they're billing you is for energy. Okay, they're billing you for energy, which is that's all they're supplying to your household is energy. So when you see your bill comes in kilowatt hour, don't get confused. It's just basically energy, because remember, power is in the unit of power is watt. So kilowatt is really power, and power is energy divided by time. And then when we talk about hour, hour is another time. So it would be energy per unit times the time canceling. All you have is energy. So you're going to see that on your electric bill. Don't be confused. Okay. Again, the utility company, when they come to your house and they hook you up to the grid, and either 110 or 120 volts. That's the electric potential difference. Okay? That is the electric potential difference. Okay? And remember, when we talk about the electric potential difference, the definition for that is change in the potential energy per unit charge. So if you remember earlier lectures that we gave, the the electric potential difference, which the volts is the same thing as the electric potential difference. The definition for electric potential difference is the change in potential energy per unit charge. And what we're talking about is if you have a circuit and you have a positive test charge, and the closer that positive test charge is to the positive terminal, the more electric potential difference it's going to have, because it's going to have more potential energy per charge. Okay, the further away it is from the positive terminal, the less potential energy it's going to have. We'll come back to that, but those concepts have to be clear. Again, when we talk about power, remember when we say power is energy per unit time, the rate at which energy is delivered or supplied by a circuit, or the rate at which energy is consumed by a load. So it is energy, power is energy per unit time. Okay? Current. Current is the rate the rate of flow of charge, the rate at which charge flow, which charge is Q, and when we say rate, it's per unit time. So current is the rate of flow of charge. Remember, the analogous that we had was, if you have a water park, the water flowing through the water park is analogous to your electric current. The water would be similar. The water would be analogous to the charge. Okay? So the current is the rate of flow of charge, the rate at which charge flow. So it is charge per unit time. Voltage, or the electrical potential difference. The electrical potential difference is the change in potential energy per unit charge. These are concepts that we discussed earlier on. Okay, so these are these are equations that we already established. So we can substitute in this equation. We see that energy is equal to volts, which is electric potential difference, times charge. Okay, and if we substitute energy, which is V times Q, in this equation, so E is V times Q divided by time. Again, if you look closely, you see that Q over T is equal to I, current. Current is equal to the rate at which charge flows. Current is the rate at which charge flows. So it will be charge divided by time. So if you plug these in the equation, you get power equal to the electric potential difference, or volts, times current, I. This is a very important equation, so you have to remember this. The power, which is equal to the rate at which energy is supplied to the circuit, or energy is consumed by the load. When you use these two other equations for current and potential difference, you plug it in the equation for power, you get power equal to electric potential difference, the volts, times the current. P is equal to VI. Very important. Okay? Very important. All right. So we have a few questions, and let's look at these questions. All right. So a current is said to exist whenever, which is correct. A wire is charged. A battery is present. Electric charges are unbalanced. Electric charges move in a loop. Again, current is the rate. At which charge flows, or the rate at which charge flows. So electric charge have to move for you to have a current. Okay, very important concept. Current has a direction by convention. Current is in the direction that. All right. So these are very important ground concepts. Now, the charge, as we said, the charge is going to move from the positive terminal to the negative terminal. Okay? So by convention, current is the direction that a positive charge moves. Okay? By convention. So when you have your electric potential difference, you have your battery, whatever power source, you're going to move your positive charge from the negative terminal to the positive terminal. Okay, then that positive charge is now going to flow from the positive. It's going to flow from the positive terminal to the negative terminal. Okay, so by convention, current is in the direction that the positive charge moves. In actuality, what really happens though is the electrons are going to move from the negative terminal to the positive terminal. By convention, that's what happens. In reality, that's what happens. But by convention, when we talk about current flowing, we're talking about the positive test charge moving from the positive terminal to the negative terminal. And then another concept that we develop is drift velocity. And what happened when you have a circuit, again, the current is going to move from the positive terminal to the negative terminal. But in actuality, the electrons are going to travel from the negative terminal to the positive terminal. These electrons are going to travel super slow. They travel exceedingly slow because they're going to be bumping into atoms. They're going to change their directions and stuff. And they're going to travel very slowly to the positive terminal. So these electrons move very slow, all right? All right, so if an electric circuit could be compared to a circuit at a water park, then the current would be analogous to the gallons of water flowing per minute, all right? That's by definition, that is what the current is, all right? All right, so we're gonna talk about batteries, and batteries is just a collection of reactive chemicals. Okay, it's a power source. It's an energy producing reaction to pump the positive charge from the negative terminal to the positive terminal. Okay, so again, it's a collection of reactive chemicals, oxidation, reduction, that produce energy. You need energy in order to get your electric potential difference, because you have to move, that positive charge. You have to move the positive charge from the negative terminal. Remember, that negative terminal is going to pull it, so you need energy to move it away. And also you're moving that positive charge to a positive terminal. It's going to repel it. You need energy. So that is why, your battery or your power source, it's just to create that electric potential difference. Once you create the electric potential difference, you need nothing more. Okay? The natural tendency is for the positive charge to flow through the circuit towards the negative terminal. That's what's normal. That's what will happen naturally. Okay, and then when we talk about voltage drop, it's just a loss in your electric potential as the charge passes through an electric device. So when you have any electrical device, a washer, or water heater, a lamp, there's going to be a voltage drop, which is a loss in your electric potential as the charge passes through the electrical device. Okay. Now we're going to come on to the definition of resistance. Now, when you have your external circuit, so you have your power supply, you have your external circuit. That external circuit, which is usually made up of wires, there's going to be some amount of resistance to the flow of the charge. There's going to be some resistance to the flow of charge in those electrical wires. Okay? Now, what is causing the resistance to the flow of the charge? Again, remember what we said, the hindrance to the flow of the charge, because as we say, by convention, the charge is going to move from the positive terminal to the negative terminal. But in actuality, what is happening is electrons are going to move from the negative terminal to the positive terminal. Those electrons are going to collide with atoms. Okay, so they're going to be bouncing all over the place. So then they're not traveling in a smooth, uh, straight direction. They have an haphazard movement. What we know is similar to the water park, the resistance is dependent on the length of the wire. So the longer the wire, the greater the resistance. So the resistance is directly dependent on the length of the wire. So if you go to a water park, okay, the resistance to the flow of the water is greater the longer the park, the water park. It also depends on the cross-sectional. It's inversely related to the cross-sectional area of the wire. So similar to a water park, just think about it. If you have water in a tube, and the tube has a very large diameter, the resistance to the water flow is going to be less, as opposed to you have a tube with a small diameter. The resistance to the flow of water is going to be greater the smaller the diameter of the tube or the water column. So what we know is that resistance is directly proportional to the length of the wire, and it is inversely related to the cross-sectional area or the width of the wire. So the larger the wire, the lower the resistance. The smaller the wire, the greater the resistance. And it also dependent on the composition or what the material that the wire is made of. So if you were to write an equation, and you can write an equation to represent resistance. So if we say resistance is R, so the resistance is directly proportional to the length of the wire. So the longer the wire, the greater the resistance. Resistance is also inversely proportional to the area, cross-sectional area. So if it's inversely proportional, so it's 1 over the area, that's a cross-sectional area of the wire we're talking about. Okay? So it's directly proportional to the length and inversely proportional to the cross-sectional area. So we could rewrite this equation and say the resistance is equal to some constant times the length of the wire divided by the area of the wire. Okay? So this is the equation for resistance. It's equal to some constant times the length of the wire divided by the cross-sectional area of the wire. This constant is what we call the resistivity. The resistivity, and the resistivity is dependent on what the wire is made of, the composition of the wire. So this constant we call the resistivity is dependent on the composition of the wire, material that the wire is made of. Okay? So that is resistance. So you try and remember that. All right. Again, so if this was water flowing through a tube and you have a narrow segment here, this narrow segment is going to offer more resistance to the flow of water than the wider segment. Similarly, if you have a wire and there's a reduction in the cross-sectional area of the wire has less cross-sectional area here, the resistance is going to be greater, because the smaller the area, the greater the resistance, okay? Again, resistance is directly proportional to the length of the wire, inversely related to the area, cross-sectional area of the wire, and when we plug it in the equation, this constant is the resistivity, and the resistivity is essentially dependent on the composition, whatever the wire is made of, okay? And we use the symbol for resistance is this squiggly thing. This is actually the old symbol we use. We tend to use it, or we go over symbols. We use, newer symbols. So when we talk about when we put a load in a circuit, that load is going to have a certain amount of resistance. And not only that, but the wire in our external circuit is also going to have some resistance. So the unit for resistance is called the ohms, okay? The unit for resistance is called the ohms. So resistivity is just a property of the conductor or the wire. Every material has a resistivity, okay? And you can, if you rearrange your equation, then you can see that you can get the units for resistivity. So it's actually the resistance of a 1 meter long piece of wire, okay, with a cross-sectional area of 1 meter squared. So it is the resistance, okay, of a one, so you put one, the length is one, of a 1 meter long piece of wire, and this is 1 squared. So all of this is 1. So if this is 1 and this is 1, then resistivity is equal to the resistance. So that's what they're saying. So resistivity is the resistance if length is 1, the area is 1. So you don't even have to know what the statement is saying. You can just work it out. So the resistivity is the resistance of a 1 meter length, 1 meter long piece of wire with a cross-sectional area of 1 meter squared. Okay, that's what it is. And the resistivity is usually a very small number. For copper, the resistivity of copper is 1.72 times 10 to the minus 8 ohms meter. So you see it's ohm meter because length over area, length is in meter, area is in meter squared. So this will be 1 over meter. And when you put it over there, so it's this resistance is in ohms, and then you have meter. So it's ohm meter. So, just looking at, and, you use common sense, and you can see that the unit of resistivity is ohm meter because length is in meter, area is in meter squared. So the meter is going to cancel one of the meters squared. So you're going to have a meter down the bottom. So you move it over here. So resistivity is meter times resistance. Resistance is in ohms. Okay? So the unit is ohms meter. All right. So resistivity is the conducting ability of a material. So when we talk about the resistivity, it tells us the conducting ability of a material. Okay? And it is dependent on the electronic structure of the material and the temperature at which you're looking at it. Again, I would say that the resistance is measured in ohms. Okay? This is the symbol. Okay? So when you plug everything in your equation, the resistivity is ohm meter. Okay? All right. Now, let's talk about Ohm's law. Okay? Ohm's law. This is a crucial, our Ohm's law equation. This is a crucial equation in current electricity. electric potential difference is equal to the current flowing times the resistance. The electric potential difference between 2 points on a circuit is equivalent to the product of the current between those 2 points and the total resistance of all the electrical devices present between those 2 points. Very crucial equation. Okay, again, Ohm's law equation. Okay, the voltage or electric potential difference is equal or is equivalent to the product of the current flowing between 2 points and the total resistance of all the electrical devices present between those 2 points. V equal to IR. All right, so you have to remember this equation. All right, so you can rearrange the equation, and if you rearrange the equation, then your current is equal to the electric potential difference divided by the resistance. The current is going to vary directly with the voltage, and it's going to vary inversely with the resistance. Okay, so the current, you can see that the current is going to vary directly with the voltage and inversely with the resistance. And you can use this concept to do a lot of things. This is a very important, just rearranging Ohm's law equation, you can use this to a lot of advantage. Because, by varying the resistance, you can vary the current. So what I'm getting at is, when you have certain tools or you have certain appliances at your house. So you have a mixer. These mixer they can mix, they can chop, they can do different things. And what they're doing is just varying the resistance. Because if you lower the resistance, you increase the current, and by increasing the current, you can increase the supply of electric energy, or you can increase the resistance and decrease the current. Okay, all right. So again, I would say you can use this equation, and this equation is used in your electric mixer. You can mix, you can beat, you can do all sort of stuff. It's also used in light dimmers, because all you do, you vary the resistance and you can vary the current. All right, so you can vary the resistance. If you increase the resistance, you're going to decrease the current. If you decrease the resistance, you're going to increase the current. So you can supply more electric energy. All right. So, so you're not, so when you do these things, it's not in isolation. These are practical things. It's a practical thing. If you vary the resistance, you can change the different function of your home appliances. Okay, the dimmer, the mixer. Okay, all right. So what we're gonna do, we're gonna stop here, and we're gonna stop here.